recording. There we go. All right. So what we're going to do today is to go over the exam from last semester. Your exam is going to be next Wednesday. Okay. So next Wednesday, which is the 9th of November, is going to be your second exam. So the format of the previous exam or the one in spring was not designed for in-person test, or paper and pencil and paper, yeah, whatever. Um, so I have to change the format, but the topic would still be the same. So what you need to know would still be the same. It's just the format would not be the same because the current format makes it almost impossible to do it by hand. All right, so what I'll do is I'm going to take a look at the first questions, and you can find those questions um, in the Canvas shell. So let me find that Canvas shell first. Um, I may not have it in the Canvas shell, but I do have it here. But if you check the announcement of your Canvas shell, you also can get your own copy. You can have your own copy open on your device while you're looking at the way I answer, because that might actually be helpful, that you can focus on both the question, what it's asking, and also on how I answer those questions. So the first question is a propagation type of question. I give you a circuit, which is not necessarily a circuit that you have seen in this class, but you're going to use the same idea that we have already used in this class to track down, how the states of the devices are going to change, how a change to the input pin is going to result in, the changes to the output pin, and so on. Now this one is a little bit more involved than you can do by hand in the class. So that's what I said, when I said the format needs to be changed. So we start again with a bunch of gates. Okay, we have some input pins. We have two NOR gates, I think two AND gates, one NOT gate, some output pins, and so on. There's also an AND gate, two AND gates here. And then this is the description of how the uh, various devices are connected. It's the same format that we have seen in the module itself. So the question is, um, analyze the circuit. First, assume that you know nothing about the states of the devices. So everything starts with an unknown state. Start with the following known states of the input. Okay, so B is 1, H is 0. Explain your answer in NC-PD phases. NC is node connectivity. In other words, we use the node connectivity to spread the state of one thing to other things. And then PD is propagational delay. So that means we are looking at the function of the devices so that we can use the input of a device to infer the output of the same device. So in this particular case, I am definitely separating the NC, which is based on how the circuit connects the components, versus the behavior of each device. So a NOR gate behaves differently compared to an AND gate, and AND gate is different from an OR gate, and so on and so forth. All right. So in the original question, I gave the class a table. This is basically a table in HTML, even though it does not look like a table. Um, but in this class, I don't want you guys to spend the time to use a ruler to kind of draw all that stuff. So I'm going to give you the table basically pre-formatted so that you can get started without having to make your own table. I have not yet decided the actual format because even if I give you the full table, it can still be taking a lot of time to copy from one row to the next, and and I don't want you to I don't want your score of this exam to depend on how fast you can write. Okay, that's not a good way to assess, right? So I'm gonna have to change the format. I have not yet decided how to do that. All right. So what I have done, before this class is I made some preparation. So this way, I'm giving you something like this. It's color coded. I know some of you are very opposed to color coding because you prefer to see a diagram. So for those of you who prefer to see a diagram, you can make your own diagram during the exam. Okay, that's not going to take a whole lot of time. This takes a lot of time. Okay, so let's go ahead and track down, what we need to do. So I'm going to have to flip-flop a little bit between this and also the question because now I need to go back to the question. to find out, what is the first state. In other words, what are the pins? So B equals to 1, X equals to 0. So I'm going to write on the tablet first, and then we'll switch to the tablet so you can see what I just wrote. All right, so I have to locate B dot port and make that a 1, and then locate H and make that a 0. So both of those are input pins. So let me switch back to the other one so you can now see what I mean by that. And let me see, where's that screen? Oh, I just passed it. There we go. Okay. All right. So I also made this, so that you can. Oh, that is not tracking. Or am I using? Oh, I was using the wrong device. Never mind. Okay. So now you can actually see my dot here. So I changed the program that I use for tracking. So this way, when I move my stylus, on the screen, you can actually follow the stylus itself. So the initial condition is we have this b being a 1, that's given by the question, and then we also have this h being a 0, that is also given by the question. Everything else are unknown. Okay, so technically speaking, I need to put question marks everywhere because that's the only two things that I know are the states of the two input pins, but everything else are basically unknown at this point. All right. So given that, the first thing we need to do, this is the initial condition, once we know the state of the input pins. So the next thing we need to do is to do a NC, which is node connectivity, spreading. So this way, okay, so I'm going to make it very clear that this is going to be an NC, node connectivity phase. So we are looking at this one is based on color, okay? I hope nobody is colorblind in this class. I think I asked that before because if someone is colorblind, it can be very difficult to differentiate some of the colors. But since no one told me that he or she is colorblind, I'm assuming that we can all kind of differentiate between all the different colors. So we start with B, okay? Because B is the one that got updated first. So now we have to look at all the orange ones and say they all have a value of 1. Is that okay? So NC is about color coding. If one of the things in a particular color just changed, spread it to everybody else of the same color. Good? All right. But that's not the only thing that got a value because we also have H, which is gray in color, getting a 0. So that means everything else that is gray would also get the same 0. Do we have any questions about this phase? Okay. No questions? It's all getting recorded too. So if you have any questions, you can always kind of watch it again and then ask me those questions. Today I don't have any lab planned for today. So that means if you have any questions about any step of the practice exam, you can use the lab time to ask me additional questions, and I'll be more than happy to kind of further explain any of the answers. Okay, but everything else would still be the same as before because they are not part of the colors. Oh, I just missed one, didn't I? Because that's also a gray one. I just missed this one here, which is also supposed to be, because of this gray getting a 0. This gray is supposed to be getting a 0 too. It's all because of this one getting a gray. This gray getting a 0 first. Okay, purple we are safe, blue we are safe, red we are safe, purple, yellow, red, light blue, green. Okay, so does that explain what NC is about? Okay, if one of the things of a color changes, follow the rainbow, so to speak, and change everything else of the same color to the same value. Okay, so now we are ready for PD. Okay, the next stage is a PD. So PD basically has to do with if we know the changes of if we know the inputs of some of the devices, can we deduce the output at this point of time? Okay, so that depends on what kind of gate we are talking about. If you have a AND gate, which has two inputs, it behaves differently compared to an OR gate, which is also different from a NOR gate, which is also different from a NAND gate. So now we have to actually look at, okay, so what gates are we talking about? Um, and we focus on the things that have been changed. So this one has been changed before. It's an AND gate. And in fact, for this AND gate here, both input pins were changed from before. So now we have a 0 for the first input, we have a 1 for the second input, and this is a regular AND without the initial AND. So this is not a negated AND gate, this is just a regular AND gate. So can we determine the output here for this particular AND gate? Let's think about it.
Yes, yes.
Yes. Okay. So what would that be? We have 0 and
It's
1.
zero.
It's just 0. Very good. Okay. So we have to be super careful, right? And this is also a change. So I'm going to use an underline here to indicate this is a change from before. The inputs do not change, so I'm just going to copy those. Let's see. Let's look at the NOR gate here. Okay, this is the NOR gate. Both inputs were question marks. They did not change, so nothing got changed here. So nothing is going to get underlined. This is an input pin. We just copy that. Input pins are pretty easy to work with. Okay, so now we have this is a NOT gate. With this particular NOT gate, we have one of the input pins changed from a question mark to a 1. So that means, I probably need to think about the output. So what would be the output of this NOT gate? If the only input is a 1, what would be the output? It would be a 0. Very good. But 0 is a change from unknown. So I'm going to underline this one. This one here is just going to be copied without the underline. This is an input pin. Input pins, that once we start the process, the input pins do not do anything. This is a NOR gate. The two inputs of the NOR gate did not change. They remain as unknown. So the output would also remain as unknown. So there's nothing we can do here. Just copy the question marks. This is the output pin, and output pins don't do anything during a propagational delay. None of the pins would do anything in the propagational delay because pins are not devices. They do not have a specific behavior like, oh, if the inputs are this, the output is going to be that. Nope, pins are just, terminals. All right, so we have this AND gate here where, one input has not changed. It remains just as a question mark. The other input went from unknown to a 0. So the question is, can we determine the output even though one of the two input pins is still remaining unknown? So what should we do here?
You can say it's 0.
Yep, exactly. Because in order for the result of an AND to be a 0, we just need at least one input to be a 0, which we have here. So that means we can indeed make a conclusion and say, the output of this AND gate is going to be a 0 because we already got a 0 as one of its input. Okay, all right. And this is a yellow thing, which is an output pin. We just let it say, okay, we don't know exactly what it is yet. So that's the PD, or the propagational delay phase. Are we doing okay so far? At least being able to differentiate between the NC and the PD and what each line is doing. We good? Okay. So the next one is going to go back to an NC. In other words, this time we look at everything that is underlined, and then we ask, let's go ahead and update everything else, of the same color. So we only have to focus on the underlined values. So this purple one is underlined with a 0. So that means, I'm going to repeat that. But everything else that is of the same color would also get a 0 at this point. And underlined, okay? So don't forget underlining as you copy the value to all the other columns of the same value. So I think we only got two of the kind of purple ones. What else did we change? We got a light blue one that got changed. See how this got a 0 here? And now we copy this one over, but we also have to update this one because it also got changed because of node connectivity. And I think that is all that we can copy, okay? Because, there's nothing else. So everything else is just, from exactly the same as before.
The green one, yeah.
The green one? Oh, right, you're correct. Okay, so the green one here is also a 0. So that means this one here needs to be changed. Um, I'm just gonna write over it like this. Because if I erase, it's gonna erase the highlighted the color as well. I didn't separate the whole thing into multiple layers. I should have used one layer for the highlighting the color, and this way I can correct the writing without erasing the background color. Okay, well, thank you. I forgot about that one. All right, so everything else are still going to be remaining the same. This is still one, still one. This is a zero as before, question mark, question mark, question mark. This is still going to be a zero, and this is going to be a question mark. Okay. All right, so now we are back to a propagational delay phase. Okay, so we go back to a PD. So with a PD, you are looking at devices, you're trying to look for devices where at least one of the input pins has changed. Okay? So we focus on devices. So the input output pins, they're not going to be important in this particular step. So we can see the NOR gate, okay, which I name A, has one of the input pins being changed. Okay, let me point out which one we're talking about here. This guy here. So it got changed. So now I want to see if I can determine the output just because one of the input pins is now known. The question is, can we make that determination? This is a NOR gate, which is a negated OR gate.
Yes, we can make a determination.
Okay, so what would be the output if we can indeed make a determination?
It's true, correct? It's true when it's false when it's 1-1.
That is true. Okay,
And
it
that's the
is
only case where it's true, right?
no, because it's a negated OR. So if you think about the regular OR, if at least one side is a 1, the output is guaranteed to be a 1.
Right.
You need both inputs to be zeros in order for the output to be a 0 for a regular OR gate.
Right.
So that means knowing only one input is a 0 is not
Not
enough.
enough.
That does not give me enough information.
Gotcha.
So it would still be undetermined. So this would still be undetermined because even though we know this is a 0, this is the problem because we don't know what the second pin is. We don't have the state of the second pin. All right, well, that's one. If you have a gate where the output is changed from the previous one, that one is not going to be a concern. Okay, so we're just going to copy everything down here without the underline anymore because it's the output from the previous phase. The NOT gate is kind of the same deal. Okay, you'll be just copy everything. This particular NOR gate is kind of in the same situation as the first NOR gate. One of the input pins got changed from unknown to a 0, but the other one remains as unknown, which means we still don't know what is the output. So we have to basically say, even though one of the pins is changed from unknown to known, we still cannot determine the output. Yep, go ahead.
So for NOR gates, it's if we see a 1, then it's guaranteed to be 0. Right? If
That
one of the pins are
for a NOR,
for a
if
NOR
we
gate.
see at least one input to be a 1, then we guarantee the output is a 0. That is correct. Yeah, yep. All right, so moving on to the AND gate, okay? So this AND gate, even though we now know the other input pin is also a 0, well, that doesn't change anything because we still know the output is unchanged as a 0. So we are not going to copy the underline over here because it is not a change. And then for everything else, we just copy from what it used to be. So that's a copy, that's a copy, this is a copy, and this is also a copy. So the question now is, well, did anything change because of this propagational delay? The answer is nope, we have reached a steady state. Okay, so let me just pause here to make sure that everybody understands why we have reached a steady state, which means there are no more changes to propagate any further. Everything that has to change because of the input pins being the way they are has already done. We have now gotten to a point where things will not change any further. Are we okay with that? Yes? Okay, all right. So now we go back to the question. And, okay, where's my question? Right here. And let me get rid of the vertical tree tab. So now we are done with one step of that question. And then the second step of the question is changing one of the pins to a different value. So comparing to, so now it is having B as a 0. So B is the one that got changed because H was a 0 to begin with. So B is the one that got changed in this case. Are we okay so far? Okay. So now we go back to the table, and now we say, okay, so this time this is a change. Put an underline when it is a change. It's just so that we are clear. And this is for step one or 0 if you want. This is for step 2. So in step 2, everything starts over there. Everything else, I'm just going to copy from before without any underline. Now, if you want to save time, you can basically combine this step with the NC, but I want to separate everything because I got time to explain this. But when you don't have time because you're answering this in an exam, you can compress the step, how you change the input pin to the first NC so they can be rolled into one single row. All right, so now we have an NC. Okay, as I said earlier, this NC step can be combined to the previous one, which is the change of the input pin. So tell me again, what is the NC? What do we do in the NC mode?
We are
Follow the rainbow, which means
change everything with the same color.
exactly. So if you see something change, they'll update everything of the same color to the same value, and they all need to be underlined. Okay, so we can see that here for this entire row here, this entire row, this is the only one that got changed. So I'm going to locate all the orange columns. Okay, another orange column here, another orange column here. So they all got changed to the same value with an underline because that's an update from where they used to be before. And then for everybody else, I'm just going to copy. So as I said, and because some of you came a little bit later, this is hard to do, when everything is on a piece of paper. So I have to change the format of the test so that this is not going to be a problem. Okay, there we go. So now we're getting to the PD phase, which means we're doing a propagational delay, which means we're looking for devices where at least one input pin has changed, and we want to see if that impacts the output pin of the same device. Okay, so now we are looking for changes to input pins only with the values that are going to underline. So once again, an input pin, we don't care. Okay, there's no such thing as a propagational delay with an input pin, so that's not a problem. Well, with this AND gate, we are changing one of the input pins from a 1 to a 0. So this potentially would be something that got its output changed. Unfortunately, in this case, the output remains as a 0 because we can say 0 and 1 is a 0, but 0 and 0 is still a 0. So it did not get changed. Okay. So disappointing here. The other one is the NOT gate here. So with the NOT gate, it used to be a 1, now it is a 0. So after a certain delay, the output of the NOT gate is it going to maintain its output or is it going to change? It's going to change to exactly. So when we change to a 1 here, the 1 is different from what it used to be, which was a 0, and that's why it is underlined. But the input is not changed. All right. So have we tracked down every single device that has at least one input pin changed?
No, there's still that N1 for that NOR gate C. Just to copy
Um,
it over, the zero.
oh, everything else we just copy. I just want to make sure that I'm not forgetting any devices that has at least one of the input pins changed. I don't think I have missed anything. So if you look at this NOR gate, these two inputs have not changed. If you look at this AND gate, neither of the input has changed. So we only got these two, right? The AND gate here, and the output did not change, and this NOT gate here where the output did change. So everything else we just copy. So we have 0, 0, question mark, 0, question mark, 0, question mark, question mark, 0, 0, 0, question mark. There we go. Um, so now we are getting back to NC. which means, NC is to follow the rainbow. So in this case, there's only one thing that we need to follow, which is the only one item that has an underline here. So the light blue one has a one, and we want to spread that to all the other columns of the same color. So this is the only column that has the same, light blue color. So we'll put a one here, and that's it. Okay, that's all we need to do with the NC face. So everything else we just copy from before. There's a shorthand version of this, but it's harder to track, which is not to update a cell unless it is an update. But I'm not gonna do it this way, that way, at this point. Okay, so this is an NC, and now we're getting back to a PD. Oops, Control Z. There we go. So now we're getting back to a PD, which is tracking down all the inputs of the devices. If we see one device with one input change, we want to evaluate whether the output is going to be changed. So this is the only input of this AND gate that got changed. Nobody else has the input changed anymore. So now we look at the output of this AND gate. Should the output change for this AND gate? Nope, continues to be a zero, and that's why this zero is not underlined. So everything else we just copy. There we go. And this is also why we have now reached a steady state, because we have followed all the changes, and all the changes have spent enough time to propagate through the circuit. And at this point, there are no additional updates possible. So I'm going to pause again to make sure that we do not have any questions at this point. So we still good? All right. And then we move on to the third step. There we go. So the third step is changing one of the input pins to another state, and this time we're changing H from a 0 to a 1. So if we get back to this diagram, this time H is the one that got changed. Okay, this is H, and that got changed to a 1. Now, if I want to combine this particular step and the NC, so I'm going to write here as step 3 plus NC. Then I just have to copy this 1 as an update to all of the other columns that also has the same color, and they all end up with the same value. So I just copy this one over here, also with an underscore, but everything else stay exactly the same as before. Oh, we have another gray one. Thank you. Thank you. So it would be helpful to indicate how many are the gray ones. Is everything matching okay? All right. And there's a reason why I use a graph paper background, because this way the lines kind of help us line up everything. All right. So now we do the PD. So the PD this time will be looking at the input pins. So I'm not going to copy all the values anymore, just so that we can save some time. So in the PD phase, we are looking at devices that has at least one of the input pins changed. So that would be this AND gate, because this AND gate has one of its input changed from a 0 to a 1. And then the other one would be this particular AND gate here, which also has one of its inputs changed from a 0 to a 1. So now with this PD, I'm going to have to specify what is the output here. This is the first one. Would it change from before? Nope, because it becomes 1 and 0, which is still a 0. So if it's not a change, I don't even bother to write anything here. But if you want to write something here, that's okay. Just do not underline, because it's not a change from what it used to be. But the second AND gate is different, because with the second AND gate, we still have a 1 here. And now the second input is also becoming a 1. So now we have and 1, which means we now do end up with a change from a 0 to a 1. So this one does need to be underlined. And then nothing else is going to be impacted. So that means this is the entire thing about the PD. So now we do the ANSI, the node connectivity propagation. which is to copy things to the same color. The purple one, I'm not concerned because the purple one is not updated, and as a result, everything else of the same color is also not updated, not an issue. The green one, on the other hand, is updated. So in the NC phase, the green one also needs to be updated over here. And I'm just going to copy it down here too because that makes it easier, makes it stand out even more. Um, and now we have another PD. And this PD has only one device that has one input changed, and that has to be this NOR gate. So now we get back to what you said earlier. Can we determine the output of this NOR gate only the first one, which is NOR gate A? So can we determine the output because we just know one of its input pins is a 1?
We can't.
Yep, and it would be, the output would be a 0. That is correct. Because, huh?
Oh, no, I was lost.
Oh, okay. So this is going to be a 0 now, and that's a change from the unknown. Um, hmm? Oh, on the red one. Yep. Yep. That's the output, and that becomes a 0. And that is a change because it used to be a question mark. So it is indeed a change, and that's why it is also underlined. Um, anything else?
So we're gonna change, oh, are we still just looking at that line? Cause I was gonna say, are we gonna change the red?
The
So
red?
all the reds because we now
You
know.
can, if you want to combine the PD and the NC, then you can also update all the reds in the same, in the same phase. But if I want to separate it, then it would be the next row
Mhm.
to update all the other reds. So this would be a 0, and this would also be a 0.
Gotcha.
hmm And in this case, would that change the output of anything? So I have to scroll down, and this is going to be tricky because if I scroll down, you won't be able to see. Um, I can scroll down a little bit, but not a whole lot, because otherwise you cannot see the top row, so we don't know what devices we're dealing with. All right, so now we are in a PD again, and we're looking for changes to input pins. This is a change to an input pin, so this particular NOR gate now has 0, NOR 0, right, which is a 1. So now this becomes a 1. It is changed from before. It has to be underlined. We are looking at this NOR gate. This is an output pin, so it's not a concern because with an output pin, it doesn't respond to propagational delays. Is that okay so far? Um, are we done yet? Can we say this is a steady state? If we cannot say this is a steady state because we just experienced one of the output devices, the output of one of the devices got changed.
So because the output for NOR got changed for C, that means the input pin, the first input pin 1 for A has to change.
Right. So now we do an NC. Okay. So now it's going to get harder because I can't see the devices anymore. They just scrolled off the screen.
Can you zoom out?
Hmm?
Can you zoom out on it?
Yeah, I can. Excuse me. So we can zoom out and scroll back up. There we go. Can you guys still see it? Because now it's a little bit smaller. All right. So we got this one here. Now we have to do the NC, which basically spreads based on the color. So we got 3 columns in yellow, and they should all be updated to a 1 at this point. And now we also have um, changes to input pins. So for this particular NOR gate, now we have 1 NOR 1, but the output is not changed. Because in order for NOR to output a 0, we just need at least one of the inputs to be a 1. So we got a 1 before, now we have 2 ones, but it's not going to change the output. So there's nothing noteworthy to put here. And then the other one is over here, which is just an output pin. So it doesn't trigger any further actions. So that means at this point, we can now say it is at a steady state. So step four is about the same thing, but do we understand the process of doing this? I think that would be the main question. Is that okay? All right. So I'm going to move on to the next question because I do want to make sure that we get enough time to cover all the different questions. Because step four is kind of the same thing. It's just it's doing the same steps, even though the states are slightly different. Okay. All right. So moving on to the second question. So here's the second question. So the second question has to do with um, the processor. So that means you probably will find bringing uh, a diagram of the processor to be helpful. Now, can I give you one in the questions? Sure, I can just print one included in the question itself, but it's not going to be annotated like the one that you might have prepared. Does that make sense? So that's one thing that you might want to do is to annotate and add your own comments to the processor diagram. So this way it helps you understand what connects to what or what devices I should look at first and so on and so forth. So this question has multiple parts. The first part is to identify and list all the components that is going to be updated. Okay, so that would include RAM. RAM can be updated. It would include all the registers because registers can be updated. And I did not make it very clear, but this is on the rising edge. So you are only concerned about the other registers. The microcode pointer is not one of the concerns. Okay. So how do you answer this question? Oh, actually, I did make it clear. On the rising edge of the clock. This includes all the registers as well as RAM, so I'm giving you, the hint of what to look for. For each identified component, explain why you think it is going to be updated. Trace your reasoning to the bits from the data port of ROM. You may refer to these using the names of the pre-dissected microcode, which are the names of the tunnel of the diagram of the circuit. Use the following area to answer this part of the question. So what components are getting updated? So we're going to look at all of these things.
Wait, so I'm sorry, when you say pre-dissected microcode,
Hmm?
when you say pre-dissected microcode.
Okay, so to explain that, let me bring up Logisim because it relates to Logisim. And we go back to main. So microcode, each one microcode refers to one location of ROM. So that's basically what it is. Okay, so every location of ROM is known as one microcode or one slice. Sometimes I call it a slice because it's a slice of time. All right, but the diagram, in Logisim is not going to be as helpful. In fact, it can be distracting because we see all the dark green or the light green and stuff like that, which is not reflective, which is not reflecting what the question is asking. So it helps to basically make a different diagram, just black and white without all those highlighting. All right, so just by looking at the tunnels, okay, let's see if we can find the ones, okay, because it's the ones that are important. Now, not all the ones are going to be important, but at least everything that is connected to some kind of enable is going to be important. I see one right here. RIEN is a one. So now you have to ask. Now we are preparing for the exam, okay? So hopefully on the day of the exam, you don't have to ask these questions because you will know, like, oh, okay, I know exactly where to look now, okay? But today we're going to look at this and go like, okay, what does it mean when RIEN is a one, and what does it connect to? So we go back to the circuit diagram here. RIEN is this tunnel here. This is the tunnel that we call RIEN. It goes into the in EN or the input enable of the register bank. So now you can go into the register bank and you ask, um, what does it mean if this wire becomes a 1? This wire is going to enable the decoder, which means the decoder will output a 1 based on what we are selecting here. So that means we know that one of the registers inside the register bank is going to be updated. but we need to find out which one. So based on the information that we have here in this diagram, it's not enough. So we have to go back to the question, and then we ask, which register are we selecting to be updated? So RI cell is 2. Okay, so now we switch back here. So let's go back to main so they can see where RI cell is located. This is RI cell. Okay, I can't highlight it because it's highlighting the component instead. But this is RSL, which is the third pin from the top on the left-hand side. So when you go to the register bank, you go look at the pin. This is pin, the top pin, middle pin. This is the lowest pin. This is now 10, which is 2. So what is it? What is it going to do? This is a 1. This is a 2. So what do you think? Which output of the decoder do you think is going to be a 1? Yes.
The second pin, so the third from the top.
The third from the top. Very good. So it's pin 2. I would call it pin 2 and not the second pin. Pin 2. So this one becomes a 1, which means register C is going to be updated. Okay? So in your answer, I want you to at least tell me register C in the register bank is one of the things getting updated. Is that okay? And then you also want to give me a brief summary of why you think that is the case. So you can just say, okay, so the easiest way to say that is to go back to main and you basically say when RIEN is a 1 and RI cell is a 10, that's the reason why I know register C in the register bank is going to be updated. Is that okay?
That's all we have to say.
That's all we have to say because I want you to be able to associate which tunnel having which value is controlling which register so that it's going to be updated next. Is that okay? All right. Okay, so we have done just one little analysis here. These are typically not really important, register output 0 enable, because that's just the output. That's not going to enable something to be changed. Okay, it does change the routing of something, but it's not going to um, specify a component to be updated. So we are only focused on this on the ones. This is also a 1, okay? So we might want to take a look at the bit 0 of the output of the ROM. So we will track it down. The ALU is not enabled. RAM is, let's see, is RAM enabled? Nope, RAM cell is a 0, so that means RAM is not even enabled, so we don't have to, RAM cannot possibly be a part of the answer here. But this one kind of worries me, okay? This is a 1, even though it has no name for that tunnel. So what we need to do now is to go back to the circuit. And this time we are tracking down bit 0 out of the D port of RAM. This is bit 0. And it does connect to the instruction register. So the instruction register is also going to be updated in this case. Is that okay? So the proper answer is going to be 2 registers will be updated. Register C in the register bank is updated because RIEN is a 1, and also on top of that, RI cell is 10 in binary, which is a 2. And in addition, because bit 0 of the data port of the ROM is a 1, that means the instruction register is also going to be updated. Are we good so far? That would be the complete answer of the first part. All right, so with that done, we move on to the second part of the question. So the second part of the question is next, identify and explain how these components are updated. In other words, we know they're going to be updated, but who is supplying the data to update these components? So that is going to take some tracking down because now we know the register C inside the register bank is going to be updated, and it is updated because of this node here. This node is going to supply the content to update the register inside the register bank. So now the question is, but this node is coming out of a multiplexer. So which way are we switching with this multiplexer? Now this diagram is not going to help you because having our mux being a dark green or 0 is not necessarily what is in the question. So that's why I would not suggest you to print out a diagram like this with all the color coding. Instead, just something that's black and white is better. But we do know that we need to look at RI mux. So in the question, it would also tell you what is RI mux. RI mux is a zero. So that means when you track down, the input, we know that we need to track down, input zero, which goes all the way to the RAM component. Well, that's one way, right? But guess what? RAM cell is a zero. The chip select of RAM is a zero, which means RAM is as if it is not there. So that means it cannot be coming from RAM. So now we have to track down what else can be coming from. So we take a look, and as it turns out, it is also coming out of this demultiplexer, right? This is an input, so it's not coming out of the instruction register. So it does come out of this demultiplexer. So now the question is this demultiplexer even turned on? Because if this demultiplexer is not turned on, or if the select is not a 1-0, then it is irrelevant. Is that okay? Does that make sense? So now we have to go back to the question, and then there are two questions here. Is RO0EN a 1, and is RO0DMX a 1-0 or 2? So let's go back, and we track down, okay, RO0EN is indeed a 1, and then RO0DMX is indeed a 2. So this is how we can confirm that this output is indeed connected to this input here. Is that okay? So when you write down your answer, you can write down all the tracking, like because of this, this connects to here, because of this, it connects to here. So now what do we do? It's coming out of the register bank. So what do? We have to track inside the register bank, right? So we are looking at the top pin on the right-hand side of the register bank. So now we go into the register bank, we look at the top pin, which is this one here. It's coming out of a multiplexer. So how do we know which input connects to the output for this multiplexer? Yes?
We check the register out select.
Yep. Register out zero select because there are two outputs.
Okay.
So you're correct, but I know exactly what you meant. But we just want to be more specific. Yeah, so we have to track down what is register output zero select. So getting back to main, this is your RO0 cell or select. So now we have to go into the question again, and that turns out to be a 3, which is 1, 1, right? So now we go back to LogicSim, go back into the register bank, and say, okay, we know this is 1, 1. Okay, if this is 1, 1, then which input are we using? This is input 0, 1, 2, and 3. So which input are we connecting to the output? It'll be the third one. Oh, sorry, I made the same. It will be the bottom one, right? This is input 0, which is 0, 0. This is input 1, which is 0, 1. This is input 2, which is 1, 0 in binary. And this is input 3, which is 1, 1 in binary. So it's this one that we need to track, and that is coming out of register D. Is that okay? So what are we concluding at this point? Who is supplying the data for the other two registers to update?
Register D.
Register D from the register bank, and now we know how to answer the question. In other words, we switch back to the question here, go back to the second step. We have now identified and explained how the components are updated. But you have to mention the tunnels that are involved in the process and say, this tunnel is this tunnel is this tunnel is this, and that is how I know this particular thing, which is register D in this case, the output connects to the input of the two registers that are being updated. Are we good so far? Okay. So if you identify an issue where two components may specify different values on the same wire or node at the same time, also indicate that condition and explain why it can happen. But in this case, we do not have a problem. The third part is how components are connected with which, how components are connected, which component is connected to which component, and how the connection is ultimately determined by the D bits. I think we just explained that. Um, okay, so we are moving on to this question. Does this microcode slice, which is described over here, if you guys prefer me to give you like 7 digits of hexadecimal numbers, and you guys write out the entire bit pattern and then find out which one goes to which tunnel, I can do that too. But I would think most people appreciate that I pre-dissect the whole thing and go like, this tunnel has this value, this tunnel has this value, and so on. Um, all right. So right. Does this microcode slice remind you of an existing instruction? In other words, of all the instructions that we have already in the opcode table, does any one of those remind you of the one that we see at this point? Okay, so let's think about this. We are updating two registers. One is register B, I think, in the register bank, and then the other one is the instruction register. And the supplier is register D. Yep.
Is it kind of like the microcode slices that we had on the Excel sheet, like comp A, B, or
Sort
comp
of,
X and
yes.
Y?
Yep. So let me get to, oh, okay. I'm clicking on the wrong screen. So if you go to the opcode table, you look at all the descriptions here. Does any one of the description of column C reminds you and say, I think we're doing that?
CMP.
It's not CMP. It's on the screen already. Okay, so
So
which one is? I'm using one register to update another register without the involvement of RAM at all. So if it is without the involvement of RAM, that means the reference cannot be anywhere of the description.
is it JMPI? Because it's
No, no,
updating that
no.
where
JMPI
the
involves RAM because it has a dereference. We know RAM is not active, right? Because RAM cell,
right.
is a zero, so we are not bothering to use
Oh,
RAM at all.
copy register.
Copy register is the one, yes. So we are actually the closest one to what we are doing is this guy here, because we are using one register to update another register
Right.
without using RAM whatsoever. There's no dereference whatsoever. Yep, so that would be the correct answer. It is indeed the CPR instruction, the copy register instruction. But that only answers one part of the question because I also want you to tell me what would be the X in this case and what would be the Y in this case. So which register is being changed and which register is providing the value to change the other register. If I remember correctly, I could be wrong. Register B is the input, that's the one being changed, and the register D is the one supplying the value, right? So if you go back to the mnemonic, which is the cell that is being highlighted right now, um, oh, sorry, not that one, but the other one, this one here. What is going to be X?
X is going to be register B.
X is register B and Y is register D. That is correct. So that would be the answer for that part of the question is CPR B, comma D in this case. Then you guys would be asking, but what about the instruction register? Well, you can actually update something and it doesn't hurt the operation. So I'm asked that's why I'm asking for the closest instruction. It's not an exact match, it just has to be the closest match. All right, so that part is done. So if I go back to the question, which I have lost track already, where did I put that? Uh, right here, the second one. There we go. All right, so now we are almost done. We just want to get the opcode now. The opcode is the all the zeros and ones, right? So that also comes from the opcode table. So this is going to tell you what the opcode is supposed to be. So what do you think is going to be the opcode? If we want register B as X and register D as Y, what would be the pattern of XXYY?
We have to scroll up and see what register is.
You could, you could. Yep.
Register is to which. So we're using O1 and B. So it'll be 0101, and then it'll be 0111.
That is correct. Very good. Okay. Because 0101 has to be here. That part cannot be changed. It does not depend on the registers at all. And then the XX is trying to specify register B, so that means it is going to be 01. And then the YY is supposed to specify register D, so that means it's going to be 11 over here. So that means it is indeed, as you said, 0101, 0111. So that would be the answer to the last part. That's the opcode corresponding to the CPR B, comma D instruction. All right, so do we have any questions about number two? So number two is basically playing detective based on all the bits. You try to play detective and go like, okay, so what are we trying to do with all of these specific bits, specified to all the different tunnels? It's doing the reverse of what we normally do, because what we normally do is I give you the instruction, it has a very specific thing that it needs to do, and then we are trying to determine, how to, switch the multiplexers and the demultiplexers and which register to enable. This is doing the reverse. I'm giving you a configuration, and I want you to describe what exactly is it doing. Is that okay? All right. So now we are ready to move on to the last question, which I think most people probably would have forgotten most of the material for that question already, because it because it has to do with floating point numbers. Okay, the double format. All right, so let me read the question first. The positive negative exponent lab assignment asked you to write the code in the subroutine E10 to exponent 2. You can refer to the baseline code in order to convert a value represented by a structure as follows. Okay, so this is straight out of the lab itself. The criteria of the input are as follows. Number coefficient should have your bit 63 set of the output. Sorry, I said input is actually the output. The value being represented is preserved as much as possible. Member E10 should be 0. You look at these and go like, well, that looks really familiar, because that's exactly what I asked you to do for both the negative and the positive exponent assignments. So the actual question starts with this. Starting with a value of V, which is 54.125, and if somebody were to ask, which base is that in, what do you think is the answer? It's base 10, because if I don't specify the base, if it doesn't start with 0x, then it is by default base 10. Express V in base 10 scientific notation as a string, such as the one used in the positive and negative exponent lab / assignment, where the coefficient is normalized. For example, 9.87 E13 is 9.87 times 10 to the power of 13. So this is where you put the answer. How do you express V in base 10 scientific notation with a normalized coefficient? Yes, go ahead.
Um, so are we gonna say 5.4125? And then I don't know the exact base, but because
E
we
is,
moved over.
okay, E is really just the abbreviation of times 10 to the power of.
Right.
So
So if we moved over to the left one, it's only gonna be, E to, I guess I don't understand. To normalize, are we moving it to like 5 point something, or we're
yes,
keeping
so
it
that is
5?
correct. So
Okay.
you're doing the right thing to the coefficient.
Okay.
But when you move the decimal point to the left with the coefficient, what are you doing to the overall value?
You're dividing it by 10.
Yes. So how do we compensate by adjusting the exponent of 10? What do we need to do with the exponent of 10 to compensate for that
You need to
division?
increase
It by 1. Okay, very good. So that means if for this particular question, it becomes 5.4125 E1. Are we good so far? All right. So that would be the answer to this part of the question. If this notation is specified on the command line of the positive or negative exponent lab/assignment, what will be the values of the members of the structure pointed to by Pn at the entry point of the subroutine of exp10 to exp2? So at the very entry point of the subroutine that you were supposed to write, and it's not supposed to be exp10, it's supposed to be e10, but that's just a minor thing. So the question is, what is the sign? Sign is 0 because the value is not negative. What about the coefficient? This is going to be the tricky part because the coefficient has a type of unsigned. It's in fact it is u in 64 underscore t. So what would be the value of the coefficient?
So it would have to be 54125.
That is correct. It's 54,125. Okay, very good. That's exactly what it's supposed to be. Then what is going to happen to E10?
E10 goes up or goes down by one, two, three, four. So it would be E -3.
Yes, that is correct. So E10 is going to be a -3, which means the negative exponent code is going to kick in, right? But that is not what this part of the question is asking. We just have to say E10 becomes -3. What about E2? Remember, this is at the very entry point of the subroutine. It's supposed to be 0. Exactly. Very good. So that is the answer to this part of the question. Um, I want to write it down. This way, when you watch the video again, you have that available. So let me go to mouse pad. All right, there we go. All right, so we know that sign is a 0. Coefficient is 54125. Okay, equals to 54125, and it's in base 10. E10 is -3. Whoops. And then E2 is a 0. That would be the correct answer. Okay, very good. Okay, I'm so glad that you guys are still retaining the knowledge from that assignment. All right, next step. Depending on the value of the member E10 of the structure pointed to by Pn at the entry point of the subroutine, this input should be processed by the positive exponent or the negative exponent code as described in the labs. So we know this is going to be the negative exponent. When E10 to exp2 is about to return, assuming the function implements the logic described by the lab assignment correctly, what are the values of the members of the structure pointed to by parameter Pn? So I want you to do this using a calculator. Okay, you can bring any scientific calculator with you. I would certainly think that log is going to be important. Exponent is going to be important. So I would definitely bring a scientific calculator and not just a plain calculator that people use just for multiplication and addition, subtraction and division. All right. Um, you do not need to use a computer to figure this out. In the following space, explain how you would do this manually. You can use numbers in base 2, base 10, or base 16, but use the proper notation so there's no confusion. In other words, if you want to use base 2, tell me it is a base 2 number. Okay, those zeros and ones are a part of a base 2 number. If you want to use base 16, start with 0x. Okay, so it's in hexadecimal. You probably want to use base 16 for the coefficient. Um, I mean, it's up to you. So now you have to show me the steps and also give me the final answer. All right, so this is the step where most people go like, well, without running the program, how am I supposed to know? And I don't even have a spreadsheet available to me, so how am I supposed to work this out?
Gotta do the math by hand.
You're going to do the math by hand. The question is, how are you going to do that math by hand? Okay, so I will teach you guys how to do this, okay? And because this is the question from spring 2022, you can kind of count on your questions would not be exactly the same. But the method, what you need to know, would still be the same, okay? So that part is still common. All right, so let's go back to this one here. So the value we want to represent is 54.125, okay? This is the value that we want to represent. So all the other stuff before, is just really try to say, okay, do you know how the program worked, the one that we dealt with before. So when we look at this value, we can now say, can we convert this base 10 number into base 2, just right here? In other words, we are asking, can you re-express 54.125 in quantities of powers of 2? You go like, yeah, it's just kind of tedious, but yes, we can do that. So we just start with a 54 and go like, 54 has a 32. After that, it also has a 16. So now we have 48 taken care of. We have 6 left. So the 6 is going to have a 4 and a 2. Is that okay? Does everybody understand, that 54 itself can be rewritten as this particular sum? They're still in base 10. I haven't done anything to base 2 yet, but these are powers of 2, okay? So that's the whole thing, right? Because we want to find out what powers of 2 do we need to make up for the same value. And then that 1.125, that is less than a half, it's less than a quarter, but it's exactly 1/8. So we say, okay, is that okay so far? All right. So the next step is to look at each one and go like, um, 32 is a power of 2, so I can probably convert this into binary really easily, right? Because the number, okay, let me try to rephrase it. The power in base 2 is the number of zeros that you need on the right hand side of the 1. So that means that this is 2 to the power 5. So that means we need 5 zeros. That would be the 32. And then the 16, okay, I'm going to use the next line for the 16. 16 is 2 to the power of 4. So I need a 1 with 4 zeros to the right-hand side. That's the 16. And then we have 4, which is 2 to the power of 2. This is the 2. And then finally, we have the 2, which is 1, 0. And then we have the 1. The 1 is just 1 because it's 2 to the power of 0. So that means we have 0 zeros to the right hand side of the 1, and that's why it just stands on its own. Okay? Hmm? Oh, wait. The next line is the 1/8. So now how do we deal with the 1/8? This is where we put the point. Remember, the job of the point is simply a separator. Its only job in its entire life is to say, on this side, we got 2 to the power of 0. On this side, we have 2 to the power of negative 1.
So
That's its only purpose of life, right?
0.001?
That is correct. We got none of the half, none of the quarters, but we got one of the eighths. And this is also in base 2. So how do we add up all of these binary numbers? If somebody's thinking, oh man, all the carry stuff, I mean, are you kidding me? No, we don't need any carries. Why don't we need any carries? Exactly, so because every row only has one, and we can only have one up to one for every single column. So there's no chance of carrying whatsoever. Yes, go ahead.
Sorry, it's
You first, and then you.
it's just you put base 1.
Okay, and Marcus?
So I still don't understand why is there a one because you have 32 plus 60 plus 4 plus 2.
Mm-hmm.
So why is there a one? Where's the one coming from?
Did I make a mistake? I didn't. I did make a mistake, didn't I?
Mm-hmm.
Very good. Okay, I did make a mistake, so I cannot even get an A in my own class.
It was 1/8.
It's 1/8, but
Oh, right.
Right, you
Okay.
added 1.
I see. I see. Gotcha. Okay, because I misread my own thing. As I said, I wouldn't be able to get an A in my own class. I would get a B because I can demonstrate with this. I can understand. I understand the concepts, but I'm just gonna like, yeah. Where did that one come from? It's the 1/8. Okay. Very good. Good job. Okay. So now we can combine all of this stuff here. So it becomes 110.001 in base 2. Okay. Is that okay? Because the first step is to convert the value into a binary representation. So you look at this and go like, but Tack, I really don't see how this is going to help me. Yep.
Right shifting?
So you think about what we're trying to do. Okay, this is already in base 2. Okay, and the power of 10 is 0. because this is the value that we want to represent without multiplying it with 10 to the power of something. Or we can say we multiply this to 10 to the power of 0. So, so that power of 10 is already taken care of. This is actually what we want in base 2. But we want to cast this in the format that the assignment or the lab is asking you to do. And what was that again? We need the coefficient to fill up all 64 bits, right? And how do we do that?
Add zeros.
Add a whole bunch of zeros, right? So what we do is we look at how many things we have here. Okay, so let me do some counting. There are 9 digits here. So we say, okay, we have 110, 110, 001 in base 2. Now we have to kind of adjust it with the power of 2, right? So this is times 2 to the power of what? Okay, so think about this. I shifted this binary point to the right-hand side 3 times. Every time I shift it to the right-hand side once, I am I have to decrement the power of 2 by 1, right? So that means right now I have to decrement the power of 2 3 times already, just like that. But this is not in the format of the lab, because the lab said, okay, give me 64 bits. This only has 9. So what do? We just have to count 64 minus 9 is what, 55, right? So we need 55 zeros, but every time we put a 0 on this side, we also have to decrement once for the power of 2, right? So now we basically end up with something like this. So we have 110, 110, 001, a bunch of zeros, times 2 to the power of -3 minus 55. Is that okay? So I'm basically padding 55 zeros over here to make up for 64 digits. Is that okay? But every time I pad a 0 on the right-hand side, I have to remember to decrement once for the power of 2. Because padding a 0 on the right-hand side essentially doubles the value of the uh, coefficient. So I have to compensate for that doubling with a subtraction of 2. But every time you decrement 1 from the power of 2, it's the same thing as division by 2. Is that okay? So your answer, this can be your answer already, okay? But if I want to be very exact, then I can express it in hexadecimal, and that's why the question said, you might want to express the coefficient in hexadecimal, because this way I can now say this is a D, 8, 8, and then a bunch of zeros, but I know exactly how many zeros I need. So the correct answer is the coefficient is going to be 0x, which is in hexadecimal, D88, followed by 13 zeros. Thank you. Very good. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And then E2 is minus 3, negative 3 minus 55, which is negative 58, I think. Yep. E10 is a 0, and sine is also a 0. I mean, these two are pretty much your given, so the only difficulty is to figure out this part. So that would be the answer. So you just saw how I did the entire thing by hand without running the algorithm at all. And that's possible because I chose a value of v that is easy to work with by hand.
Is that a hint?
Huh?
Is that a hint for the exam that you're
Yes.
not
So
gonna?
I'm not going to give you guys something that's much more difficult to do. So it will still be something that you can convert from base 10 to base 2 without having to use a calculator. So that pretty much sums up, the second exam. In spring 22, there were only 3 questions, and I intend to keep it that way, to only have 3 questions. And the scope of each question would still be about the same as last time, One is going to be about the propagation of delay with some kind of device that can remember something. The second one is going to be about the processor architecture itself. The third one is going to be about double precision floating point numbers. Do we have any questions about the scope? Any questions about the concepts within that scope? Nope. Okay. So like last time, the best study guide is your own. Okay, because everybody study in a different way. I do not work well with auditory stuff. But I like abstraction. Okay, so I write down all the definitions, all the symbols, all the definitions. Some people like pictures. Okay, so for those people, you can actually use a more pictorial representation of the base conversion thing. It works that way too. So your study guide depends on how you take in the information in class and how you prefer that information to be, what form that information should be in when you try to look it up in the exam. So we have 1 week from today, which means you got quite a bit of time to study and prepare for the exam. Oh, there's one more thing that is kind of interesting. But if you have any questions about the second exam, just let me know, and you can totally interrupt me because what I am about to show you is not going to be exceedingly important, but I think it's kind of interesting. And I need to find out where I don't have it here. Okay, that's okay. I can, oops, there we go. Did anyone go trick or treating? My kids, this is the first year that none of my two kids went trick or treating. One is 18, one is 22. I remember last year they were still coming home and they lay out all the candies on the floor, do all the trade because somebody likes this kind of candy. The other one said, okay, but I got something that I don't want, but I like that from you. Yeah, that was just last year when they were 17 and 21 respectively. All right, so if I go to the announcement, I have not checked it out, okay, but you guys can kind of look into it if you want to, okay? It's not a mandatory thing. The district, LRCCD, the Los Rios Community College District, is organizing these events. There are three. I'm not sure exactly what they're going to talk about, but each one is 1 hour, and it doesn't interfere with this class. So if you are interested or curious, okay, it doesn't have to be because, oh, I think I need this. It can be something just like, I'm just kind of curious what they have to say. So the first one is self care and time management. The second one is about understanding and applying motivation. And then the third one is about test taking anxiety, how to basically cope with that. So, I'm just giving you this information because I was told to give students this information. Any questions?
I wish they moved the test taking anxiety up to the third.
um, it's a three parts. Yep. I can tell you something about anxiety test taking anxiety because I don't have any, and that's training from early on, like elementary school, like first grade. In Hong Kong, they train you, with all of these exams, and I can tell you, in elementary school, middle school, and for the most part, high school, my score is at the bottom of the class. I'm usually within the last five students in the class if you look at my ranking. So I dealt with the anxiety part easily because I already know the outcome. It's not going to be good. So why be anxious about something that is already certain? It is already determined. So I just go like, I'm just going to go in, do my best. Whatever happens is going to happen. But with that mindset, okay, I also make sure that I really am doing the best that I can because my mind is not worrying about the outcome. I'm just gonna go. Well, I mean, whatever I can do, I'll do. But I'm not expecting too much. You can call it expectation management. And motivation in that case is just trying to avoid or prevent the wrath of my own father and also the teachers. That's not the motivation was not quite enough to actually get the performance out. But for anyone who wants to, I think self care and time management is actually important. Do you stay? Are you hydrated? Did you eat enough? Okay, did you get too much sugar in your blood before the exam? Because otherwise you get a crash, and then that's not going to be good, right? What do you eat before the exam? Having a full steak, breakfast may not be the best. Okay, but having just donuts or worse yet, bagel is also not what you want. Bagel has a glycemic factor that is higher than sugar. Let me explain what that means. Glycemic factor basically measures how quickly your body can take in the carbohydrate. So they use sugar as a standard. So just regular table sugar is 1 or 100, whatever you want to scale that, doesn't matter. So most food items, would be below that, right? Because eating plain sugar is like that's probably the quickest way to get glucose into your blood. Well, as it turns out, bagel is higher than sugar. If you eat bagel, you might as well just eat sugar of the same mass because your sugar would actually take longer to get into your bloodstream compared to a bagel.
That's interesting.
Yeah, I think that has to do with bagel is processed food.
Right.
So the particle is really, really fine, after you chew and swallow it. So
Yeah.
it has a huge, gigantic surface area, and your body just, soaks up all that glucose.
That's why bagel day at my old job is just kind of like the worst day for me
The funny thing is, this does make ice cream look really healthy.
too.
Ice cream, donuts, look really healthy, because the carbohydrate is not mostly from the sugar,
Yeah.
it's from the fat, right? So just kind of fun fact. All right. I think I'm going to end the lecture at this point. But if you want to stay and talk about, specific things, within, what I just talked about, or within the scope of the exam, I can certainly, stay and, talk about those things. But other than that, the lecture is officially over, and I can stop recording.